Everyone, in this video I'm going to talk about permutations and combinations. There's a couple of formulas up here, but I'm not going to talk about those for a little bit. I want to give you a couple examples so you get a sense of what is a permutation or a combination. In my first example, let's say we have a club. This club has 10 members, all right? So there's 10 members in the club. How many different ways could we elect a president, a vice president, and a treasurer from this 10-member club? Well, I'm going to start with the fundamental counting principle. The president. How many different ways could we elect the president? 10 possibilities, 10 different ways. Now how about that vice president? That can't be 10 because someone has already been selected right here. So now you're just left with 9. 9 different possible ways. And how many different ways could you elect the treasurer? That would be, well, now there's only 8 remaining. 8 people left, 8 possible ways. And by the fundamental counting principle, we just multiply these numbers. 10 times 9 times 8, which is 720 ways. Okay? Yeah, I didn't even use this formula. Now, if you want to use this formula, absolutely. This means how many different ways. Right here, you've got 10. P stands for permutation, and this is a 3. And we're basically saying how many different permutations of size 3 can we get from 10 different values, or 10 different elements, or 10 members. And with this formula, you would get 10 factorial over 10 minus 3, which is 7 factorial, which is 10 factorial or 7 factorial. The 7 factorial will cancel out with the 7, 6, 5, 4, 3, 2, 1 here. You know, you can imagine 10 times 9 times 8 times 7 times 6 times 5, all the way down to 1. 6, 5, 4, all the way down to 1. These would all cancel, leaving with the same answer, 10 times 9 times 8. So, but absolutely, you can just hit this on a calculator if you want. Calculators have this function right here. Put 10, hit the P. Actually, with the TID4, it's an NPR button. So anyways, that's a permutation, all right? And the ordering was important. And I'm going to extend this for a second. Let's just look at 3 of those 10 members. Let's say their names were Abe, Barb, and Chuck, okay? And A, B, and C, Abe, Barb, and Chuck. Well, just think of all the different ways we could have selected them here, or elected them. You could have had Abe, Barb, and Chuck. Or you could have had Abe, then Chuck, then Barb. You could have had Barb, then Abe and Chuck, or Barb, then Chuck and Abe. Or you could have had Chuck, Abe, Barb, or Chuck, Barb, Abe. But I wanted you to see the different orderings of just those 3 members, 3 of the 10 members. Notice we have 6 different ways here. This came out to 6 of those 720 different ways, just for Abe, Barb, and Chuck. And the reason is because with these 3 people, you know, it's like 3 times 2 times 1. Let me make that 3 more clear so you can see that. 3 times 2 times 1, which is 6. Or that's 3 factorial, which is 6. So I just wanted to let you view just, well, what if you had just 3 members from that 10 members? Well, that accounted to 6 different ways from that 720 ways. So there's a lot of different ways. From 10 members, you can elect a president, a vice president, a treasurer. I did this so you can understand a combination. See, with a combination, the order in which the selection is made does not matter. So I'm going to give you an example, a very similar example, but listen to this wording. Let's say you have 10 members. All right. How many different committees of size 3? How many different 3-person committees are possible from 10 members? Okay? So you're like, okay, 10 times 9 times 8, like before. But everyone, these are just 3-person committees. So I'm going to put this fraction bar here. We're going to divide out 3 factorial. Because think of the committee let's say it's the same people. Say we got Abe, Barb, and Chuck. Well, that's just one committee. You can't switch it around like we did over here. You can't say, well, Barb is here and Abe is here. Chuck. Does not matter. The order in which the selection made does not matter. So we have to actually divide out the 3 factorial, the 6 different ways for each group of 3 people. If that makes sense. So this is going to be smaller than that number. This is 720 divided by 3 factorial, which is 6, which gives us 120. 120 different combinations possible versus this 720. What's the difference here? Yeah, this is 120 times 6 over here. Because for each one of those 3-person groups, there were 6 different ways you could switch around the order. Here, you can't switch around the order. It does not matter. So Abe, Barb, and Chuck would be considered one of those possible committees of 3 people. Okay? Of course, there's a formula here. Very similar to this. What's getting divided out is this R factorial. So this would be, let's see, this was 10 factorial over 7 factorial. This becomes, in our problem, I'll get this out of the way, 10, you can call this C, it's combination, but you can say choose. 10 choose 3. How many combinations of size 3 can we choose from 10 members? And it becomes in this formula, 10 factorial over 10 minus 3, 7 factorial, but we have to divide right there the 3 factorial. So this is 10 factorial divided by 7 factorial times 3 factorial in the denominator. And if you hit that on a calculator, be careful. I put parentheses around this product right here, 7 factorial times 3 factorial, you'll get 120 ways. This button is also, okay, a function on the calculator. So a lot of students just use the calculator, which is fine, 10, choose 3. All right, and you hit the 10, you hit the 10 and the NCR button on the calculator, and hit 3 and hit enter, and that'll give you a result. What's most important is to read a question and understand, is it a permutation or is it a combination problem? All right, so I'm going to erase all this. We'll do a couple examples. All right, there we go. Let's say we have a horse race. All right. There's 20 horses in the race. And how many different ways could they finish in the first 3 places? Let's go like this. I'll just apply the fundamental counting principle. 20 horses could finish first place. Now you're left with 19 horses to finish in second place. And then 18 horses are left remaining that could finish in third place. How many ways can this occur? 20. How many ways can this occur? 19. How many ways can this occur? 18. I'm just applying the fundamental counting principle. 20 times 19 times 18, and I get 6,840. This is a permutation. I could have written this as 20p3 because the order was important, right? Let's say the 3 horses were Abe, Barb, and Chuck. Well, Abe could have been here, Barb could have been here, Chuck could have been here. Chuck could have been here, Abe could have been here, Barb could have been here, etc. We can switch around that order. That's why we have a permutation. The ordering was important. Now I have a different question. Let's say you have a lottery. All right? And in this lottery, there's 50 possible numbers, 1 through 50. All right? Those integers. 1 through 50. So there's 50 numbers possible to select from. All right? 50 total numbers, 1 through 50. Those positive integers. And to win this lottery, you gotta choose those 5 winning numbers. The 5 winning numbers from the 50 numbers possible. Okay? And the order in which the selection is made is not important. All right? the order in which the selection is made does not matter. So, I can do it this way. There's 50 possible numbers here, 49 possible numbers to choose here, 48 possible numbers to choose here, 47 here, 46 here. But because the order in which the selection made does not matter, I would divide out 2, 3, 4, 5 factorial. All those different ways I could have switched around the orders. This will give me my result. If I multiply 50 times 49 times 48 times 47 times 46 and divide out this 5 factorial, or divide out this 5 times 4 times 3 times 2 times 1. This is a combination because the order in which selection made does not matter. Okay? This is going to be a lot of numbers. But I can also just do this. When I use this formula, this is 50 choose 5. Alright? Which is this 50 factorial over 50 minus 5 factorial times 5 factorial. And I will hit that on the calculator. And I get 2,118,760 ways. So, in this lottery, sure enough, if I bought one ticket, I have about a 1 in 2.1 million chance of winning that lottery. Not very good. But the reason this was a combination, not a permutation, is because the order in which selection made does not matter. If I chose the numbers 1, 2, 3, 4, and 5, okay? And these numbers came out of some kind of, some kind of tube or something, or electronically, and they came out in a different order, but the 5 winning numbers were 1, 2, 3, 4, and 5 in a different order, I win. Because the order in which the selection made does not matter. Permutations and combinations. That's it.